Good morning, dear students. Today we'll continue from the portion which we have left in the last class. In the last class, we have discussed about the organometallic compounds, and mostly we discussed about the oxidative addition. Today we'll discuss about the reverse portion of oxidative addition, that is reductive elimination. And this is almost the reverse of oxidative addition. In oxidative addition, basically two new ligands were added to the metal center, and there is increase in oxidation number by 2 units, and as well as the electron count increases. And here in the reductive elimination, we can see the two ligands, they are eliminated. Now you can see from this octahedral complexes, the two methyl atoms are eliminated, and we get this ethane atom. Okay, so here the oxidation state of platinum is +4, and in the product it is 2+. Okay, so we can see the oxidation state decreases by 2 units. The coordination number also decreases by 2 units. Let us say from octahedral to square planar. So the two cis-oriented ligands, they form a stable sigma bond and they leave the metal. Now the factors which facilitates the reductive elimination. For example, the first one is a high formal charge on the metal. The oxidation state on the metal should be high, then only it can give reductive elimination. And the second one is the presence of bulky groups on the metal. Okay, if it is more bulky, then only it will favor reductive elimination to relieve the strain, and the product should be electronically stable. Okay, so this is very, very important. The cis orientation of the groups which are taking part in reductive elimination, this is must. So the groups which are to be reductive eliminated, they should be cis to each other. For example, there are 4 methyl groups over here. So let us say one of the methyl group is this one. Then the other possibilities are this and this. But this group cannot be eliminated along with this methyl, because these they are trans to each other. Because we know in octahedral complexes, the 1,6 position is trans. So we'll move to the next portion. That is some of the examples. For example, in cases like where the reductive elimination is promoted by ligand dissociation, we can have an unsaturated and more electron deficient metal center which undergoes reductive elimination very easily. For example, here it is an octahedral platinum 4+ complex is with 18 electron. So first, this polar molecule, the iodide ion, that is eliminated. So we get a 16 electron species platinum 4. So now this platinum 4, this can undergo reductive elimination. Of ethane can be reductive eliminated. So we get a 14 electron platinum 2 complexes. And the iodide, which was eliminated in the first step, this was not exactly eliminated. This is outside the coordination sphere. So now that can join to the platinum center. So we get a 16 electron platinum 2 square planar complex. So as you can see, the solvent plays a very important role in this reductive elimination step. For example, in polar solvents, I mean, we can have one type of reaction. In the non-polar state, we can have a different reaction. For example, here you can see first, let us see this, let us say this polar solvent. Let us say in polar solvent, the species is already it is already polar and there is charge separation. For example, this remains like acetate ion, and the rest of the molecule like a cation. So now from this cation, okay, so the groups which are to be eliminated are 2 methyl groups. So the ethane is eliminated and the acetate can join. Okay, so the acetate ion does not leave the metal center. But in non-polar solvent, let us say one cation, that is methyl group, and the anion, that is acetate. So the methyl acetate is eliminated. So we can have still these two methyl groups are in the platinum center. So as you can see, I mean, the solvent plays a major role in reductive elimination process. So to move next, the bite angle. Okay, so the bite angle, this plays a very major role. As you can see, this is the bite angle which a bidentate ligand makes at the metal center. Now, let us say these are phosphine examples of this phosphine. Now, these phosphine ligands that makes an angle at the metal center, which is known as the bite angle. And now you can see the bite angle. For example, we have taken two ligands, DPP and this DPPF, and the bite angles are respectively 90 and 99 degree. Now we can see when the ligand is DPP, this is 1,2-bis diphenylphosphinoethane. So here the reaction occurs at 35 degrees Celsius and the T half, you can see this is 30 minutes. But when the ligand is a DPPF, okay, the reaction can happen at 0 degrees Celsius and this is very, very rapid. So in all the cases, the methyl group and the phenyl group, they are eliminated. So the eliminating groups are same, but the bite angle is more, the reaction is very, very rapid, and this can happen at lower temperature. So the bite angle, it plays a very major role in this reductive elimination process. So now we'll move to the next portion, that is insertion or deinsertion reaction. So insertion is the insertion of a molecule into the organometallic compound, and is the deinsertion is the reverse process of that. For example, here you can see from this, let us say this starting complex, the starting complex, the first there is a migration of X over Y. Okay, so we get the intermediate. Now this ligand L can insert into the organometallic compound. So we can have this, now this new ML bond and this YX bond is there. So if you can see, mostly this is, let us see an example of, let us see this manganese alkyl bond. Okay, so this is alkyl manganese carbonylate. Okay, so you can see this is octahedral complex. Now, if you see the electron count, this is 7 plus this is 5 into 2, 10, 17 plus this is 1, 18. Now, if you want to add this phosphine, this does not undergo the addition of phosphine because this is already octahedral and 18 electron species. So what happens first? Now, this we'll see the mechanism of this particular reaction in detail after a few slides. So first, let us say this either this methyl group is migrated to carbon monoxide, or this, let us say this carbon monoxide migrates to methyl, whatever it may be the reaction. Okay, that we are going to discuss after a few slides. First, this SL group is formed. Now, this SL group is a 16 electron complex which can undergo the addition of phosphine to get the product. Okay, so let us say this X is, let us say this is carbon monoxide which is migrated to Y is methyl. So we get the acetyl complex and this L is the phosphine to get this new complex. So we can see there is no formal change in oxidation state because this was a neutral molecule. So this was, for example, if this is methyl, the metal is in +1 oxidation state. And if this is acyl, the metal is still in +1 oxidation state because this is phosphine. Okay. So a vacant coordination site is generated during a migratory insertion. During this migratory insertion, a vacant coordination site, this is, now you can see this is the vacant coordination site on the metal which is generated, and the incoming ligand L occupies this site. So the groups undergoing migratory insertion reaction, so this is more important, they are cis to each other. Okay. So these are enthalpy driven, although the reaction is entropy prohibited. Now to moving back to the types of migratory insertion. Okay, so you can see, I mean, this is either 1-1 or 1-2. Okay, so both are migratory insertion, but as you can see, the ligands like carbon monoxide, which are eta-1 ligands, they mostly show 1,1 insertion reaction. And the eta-2 ligands, just like ethylene, they form 1,2 migratory insertion reaction. So now we'll see what is the basic difference between this 1,1 and 1,2. For example, in 1,1, the two new bonds which are formed, they are formed to the same atom. Okay. The new, the two new bonds which are formed, they are formed to the same atom. Now, in for example, here we are having one, let us say this AX bond and AM bond. Okay, so basically this is carbon monoxide. Now, here, let us say we are having this A is bonded to metal and B is bonded to X. Okay, so the two new bonds which are formed, that is forming two different atoms. So we can see some examples to discuss this. Now, here you can see, let us say this is 1,1 migratory insertion. Okay, so this was basically a Dept bond. Okay, and this is a normal covalent bond, rhodium carbon bond. Now you can see we are having a rhodium carbon single bond, and let us say this CC bond. Okay, these two are new. Okay, that is forming to carbon of carbon monoxide. So the group which is migrating is carbon monoxide, and these two new bonds, this rhodium carbon and this CC, they are new. That was not present in the starting complex. Now here, as you can see, this is a rhodium carbon. Rhodium is attached to this carbon. Let us say, this is 1, this is, let us say, 2. So this rhodium is bonded to carbon number 1 and hydrogen is bonded to carbon number 2. So the two new bonds which are formed, that is two different atoms. Now you can see, a 2 vacant site is generated by this 1,1 or 1,2 insertion reaction, and this is to be occupied by the incoming ligand, which is 2 electron. And we can see this is cis arrangement is required. It is a must. And we'll see this detail of this insertion or elimination reaction, which is a reverse. Now you can see this X is migrate to carbon monoxide, and we can have this acyl, and this is the vacant site which is created, okay, which is to be occupied by this L. Now I can see the electron count changes by -2 from here to here, okay, because this is giving 1 electron, this is 2 electron, total 3, but now this changes to 1 because this acyl group is 1 electron donor. So electron count changes to 2, coordination count, electron count changes to -2 from here to here. Coordination count also changes to -1 because here this is 2 coordination. Okay, now this is 1. Oxidation state does not change because this was -1, this is neutral, so metal is in +1 oxidation state. This is -1, so obviously metal is in +1 oxidation state. So after addition of this ligand, I can see the electron count changes by +2, the coordination count changes by +1, the oxidation state does not change. You can count by yourself. Okay, it's not that difficult. So the reverse process, first the ligand is dissociated. Then there is elimination reaction. We'll see the elimination reaction in detail. And this is the, respective electron count, change in coordination number or change in oxidation state. So we'll see in detail of this carbonyl insertion reaction, CO insertion reaction. And this is the example. Let us see, we can see this example. This is what we are discussing few slides back. Okay, this is, now you can see this is 18 electron species. Now, if you want to add a carbon monoxide, you cannot have because this is already coordinatively or electronically saturated. So first, let us say we are discussing CO insertion reaction. So this CO has to insert into this MC bond. So we get the SL1 followed by the addition of new carbon monoxide. Okay. So 3 mechanisms are proposed for this. For example, direct CO insertion. That means direct insertion of carbon monoxide into the metal carbon bond. For example, we have a metal alkyl bond. So the new CO which is added, that is inserted into this metal carbon bond. So we get the SL1. The first mechanism which is proper. The second mechanism is CO migration. That means the CO, one of the CO which is cis, because this CO is trans for the metal alkyl complex. So this cannot migrate. So out of these 4 CO, one of the CO, this migrates to this methyl, so that you get the SL1. Okay. This would give the 5 coordinated intermediate. This is a vacant site, and the incoming CO joins the vacant site. So this is a CO migration. So the third one is alkyl migration. That means the alkyl group migrates to the CO which is cis to it. So for this alkyl, these are the 4 CO. 1, 2, 3, 4. These are the 4 CO which are cis. So the alkyl groups migrates to, one of these cis. So we get the SL1. So this is again giving a 5 coordinated intermediate. Now this new carbon monoxide can join the vacant site of this alkyl group. So we get the product. Okay. Now we have to see which one is the actual mechanism. The CO insertion, direct CO insertion into the MC framework, or there is CO migration followed by the incoming CO, or there is alkyl migration followed by this incoming CO. So these are the 3 examples which we have shown here. That is direct insertion of this incoming CO into the MC bond. So you can see this incoming CO is colored in green. The new CO is, this is in SL group. So the second one is intramolecular CO migration. That means the CO migrates to methyl. So you get the SL1, and this CO that moves to the vacant site. So in this, the new CO is cis to the SL group. As you can see, this CO and the SL group, they are cis to each other. And the third one is methyl migration. The methyl group migrates to carbon monoxide, which is cis to it, to give the SL1. And now you can see the vacant site is created here. So the new carbon monoxide can can migrate to that vacant site to give the product. And here you can see the new carbon monoxide. This new carbon monoxide is cis to the SL group. So now let's see, which mechanism is the actual one. Okay. So 3 experiments have been carried out to check the exact mechanism. First one, right? We have to do all these by the labeling experiment. So now you can see first experiment, the reaction of the starting material with the carbon monoxide labeled with 13C. Okay, so this gives a product in which the labeled carbon monoxide is in carbonyl, found in SL1. Okay, so the incoming ligand, there is labeling. Okay, so this gives a product in which the labeled carbon monoxide is in carbonyl, non is in SL position. Coming back to the second experiment, this is the reverse reaction. Okay, you can see the decarbonylation. Okay, the reverse of this carbonyl insertion. Now you can see this is the SL group. Already this is 18 electron. So the reverse reaction, which readily occurs on heating, is the decarbonylation reaction. Now, when this reverse reaction is carried out with the labeled carbon, this is in SL position. That means over here. Now, here the product, in this product, the labeled CO is entirely cis to methyl. Okay, the labeled CO, which is entirely cis to methyl, no labeled CO is lost over here. You'll clearly understand when you exactly go to the mechanism. The third experiment, the reverse reaction, which is carried with a labeled CO in carbonyl. The second one is in SL, the third one in carbonyl. That means in any of these 5 carbonyl. Okay, but the thing is that it should be cis to the SL group. That means 4, not 5. Okay, the product is giving 2:1 cis to trans. That means 2 portion cis, one portion trans, and you can see that cis and trans labeled to the position of CO with methyl one, and some of the carbon monoxide is lost during this process. So basically this is 2:1:1. That means two cis, one trans, and one is lost. Okay. So by conducting the experiment 1, the mechanism 1 is ruled out. The mechanism 1, what was the mechanism 1? If you remember, that is direct insertion of this incoming CO into the metal alkyl 1 to give this acyl. Okay. So by conducting the first experiment, because the first experiment says that, I mean, nothing is in acyl 1. I mean, this is the labeled CO is in the carbon monoxide, not in Sl1. So by conducting the first experiment, the mechanism 1 is ruled out. Now we have to see whether the mechanism 2 or 3 is right. So here we are discussing, I mean, the experiment 2. This is the second experiment. Okay. What is second experiment? Second experiment when the label CO is in Sl group and you heat and there is decarbonylation reaction. Okay. So by this we get, I mean, the product in which this is completely cis. Now we'll see the mechanism 2, which is CO migration, and the third one, mechanism 3, is alkyl migration. Okay, CO migration and this alkyl migration. Now you see the label CO is in acyl position. So for this, I mean, this is not the position because this is trans to acyl group. So either this. Any of these four, I mean, one of the CO is lost first, then the carbonyl migrates to that side. Okay. So now let us say, I mean, the carbonyl is lost from this position. Okay. Then there is CO migration over here. So as you can see, I mean, this is cis, the label CO and the alkyl, they are cis to each other. Okay. And in mechanism 3, so again from this, the label CO is in acyl 1. So there are 4 positions, 1, 2, 3, 4. So now the CO is lost. Now the methyl group migrates to one of the position, let us say to this position. Now you can see this methyl and label CO, they are cis to each other. So we cannot draw any conclusion by conducting experiment 2, whether the mechanism 2 is right or mechanism 3 is right. So what we need to do, we need to see the third experiment to see which mechanism is actually right. Now let us see the third experiment. What is the third experiment? If you remember, the third experiment is the label CO is in carbon monoxide, not Sl1. In second experiment, it was in Sl1. Third experiment, it is in carbon monoxide, to any of the carbon monoxide. And obviously it has to be cis to, I mean, this Sl. It cannot be trans. So we have not taken this position because neither CO or methyl from the Sl can migrate to the trans position. So we have not taken this position. So let us say we have taken the rest 4 positions. So we have numbered in clockwise. Let us say this is 1, this is 2, this is 3, and this is 4. So we take this numbering for both mechanism 2 and mechanism 3. Remember, mechanism 2 is CO migration, internal CO migration, and mechanism 3 is internal alkyl migration. Okay. So what we do, we heat it. So the CO is lost first. Then there is either carbonyl migration in mechanism 2 or alkyl migration in mechanism 3. So let us say, I mean, loss of 1, this carbon monoxide is lost. Then 2, that means carbon monoxide from position 2 is lost. Then 3, carbon monoxide from position 3 is lost. Then 4, carbon monoxide from position 4 is lost. So either from 1, 2, 3, 4, any of the position, the carbon monoxide can go. Okay. The second mechanism said that, I mean, the CO has to migrate. So the CO migrates to first position 1 over here. The CO migrates to the second position. This is the second position. The CO migrates to the third position and the CO migrates to the fourth position. Now, when there is loss of CO, I mean, there is no label CO because this label CO is already lost from number 1 position. And when the carbon monoxide goes to either 2, 3, or 4, this label CO and the methyl, they are trans, whether it goes to 2, 3, 4. Okay. So we do not get any transport product. Rather, we get 3 ratios of Cs and 1 ratio where there is no label CO. So probably mechanism 3, I mean, will be the right choice for us. So what you need to do, I mean, in mechanism 3, I mean, again, after the loss of this carbon monoxide, either from 1, 2, 3, or 4, the methyl has to migrate. Now, first the methyl migrates to 1 position. Here it is 2nd position. Here it is 3rd position. Here it is 4th position. Now, when the carbon monoxide, this is lost from position 1, so then there is no label CO. Okay. Now, when the methyl migrates to the 2nd position, the methyl and this label CO, they are cis to each other. Now, methyl migrates to 3rd position, they are trans to each other. Now, methyl moves to 4th position, they are cis to each other. So, here you can see we are getting 2 ratio of cis, 1 ratio of trans, and 1 ratio in which there is no label CO. So, we are getting exactly same as in experiment 3. We are suggesting we are getting 2:1:1. So probably, although we started with this is CO migration, so actually it is not CO migration, rather it is alkyl migration followed by next CO addition. So we do not call it is a CO migration, rather we'll call this as alkyl migration. Now we'll see this insertion of alkene into MH bond. Okay, so this is basically 1-2 insertion. So we are having a metal hydridoalkene complex. Now you can see we have having metal hydrogen bond, and this is alkene complex. So after 1-2 insertion, you are getting a metal alkyl complex. So this is a new term for you. I'll explain this. What is that? So before that, goes through this intermediate in which this MH bond is not broken. This is a bond making. This is also bond making. This is bond breaking. So this is the transition state. So we are getting the, let us say, if these are all hydrogen, this is metal ethyl group. Okay. Now this agostic hydrogen. So this, although this hydrogen is not exactly bonded to metal, but to satisfy the electron deficiency, because here we are getting 1 electron count from hydrogen and 2 from alkene. So basically 3, but here it is 1. So there is a deficiency of 2 electron. So this has been given by this hydrogen, which is agostically bonded. The agostic words comes from the anchoring, just like this anchoring. So this hydrogen is giving some electron density to the metal. Now, this is either the R equal to hydrogen or R equal to ethyl. Okay, for example, here R equal to hydrogen. So basically, this is insertion of alkene into the MH bond, or if the R equal to ethyl, the insertion of alkene is to the MC bond. As you can see, the reaction involving MH is 6 to 10 kilocalorie per mole lower energy barrier. Okay, so that's why the migratory aptitude is much higher in case of MH compared to MC. Okay. So this is another example of insertion of alkene into MC bond. As you can see, this first we are having a metal alkyl complex. Now the alkene coordinates to the vacant side. Okay, so this alkene inserts into the metal carbon bond. So we get a metal alkyl. Then there is a vacant side in which the alkene joins. So this is how the polymerization goes on. Basically, we'll see this in Ziegler-Natta polymerization. So this is different type of elimination reaction. First one is beta hydrogen elimination reaction. This is reverse of 1,2 insertion reaction. So now you can see this is alpha carbon, this is beta carbon. So one of the beta hydrogen is eliminated to the metal. We are getting this MH bond plus this alkene one. This is alpha hydrogen elimination. That means one of the hydrogen present on alpha carbon is eliminated. Okay. So this gives something like carbene. And there is decarbonylation reaction. That means the carbon monoxide is lost from a metal acyl complex. So you get a metal alkene plus metal carbonyl. So now to discuss this beta hydrogen elimination. So in beta hydrogen elimination, the reaction occurs from a metal alkyl complex having beta hydrogen, which is sigma bonded to the metal center, is converted into the metal hydride and the alkene. I can see this is the alpha, this is the beta carbon, the hydrogen present on beta carbon that is eliminated. So you get a MH bond and this alkene complex. Okay. So the metal must have an empty orbital in which the product can form, because if you do not have an empty orbital, so the reaction cannot happen. Okay, so the condition is that the starting complex should be coordinatively unsaturated, because you can see, I mean, there is only one bond. Now here there is MH bond as well as this alkene is present. So the starting complex should be coordinatively unsaturated, but there is no change in formal oxidation state of metal. For example, here it is metal is in +1 oxidation state. Here it is also +1. So if you look at the mechanism of this beta hydrogen elimination, so first from these metal alkyl complexes, you have a transition state in which the hydrogen is loosely bonded to the metal. These bonds are neither, I mean, forming or broken. Now we have a MH bond and this metal alkyl complex. So the beta hydrogen, will see the cases in which the beta hydrogen elimination does not happen. For example, the alkyl where there is no beta hydrogen, for example, in benzyl or in neopentyl, there is no beta hydrogen. So there is no question of this beta hydrogen elimination. Okay, the second case, the beta hydrogen on the alkyl is unable to approach the metal, as this is already in sp hybridized carbon. So this hydrogen, although this is beta hydrogen, but that is far away from the metal center. Okay, so this case, the beta hydrogen elimination does not happen. The third case, I mean, the MCCH, if they cannot become coplanar, so there is no question of beta hydrogen elimination. Now we'll see, I mean, the methyl elimination. For example, here there is insertion of this alkene into the metal carbon bond, particular to say metal methyl bond. So you get, I mean, the insertion of alkene into the metal methyl bond. So you get the corresponding metal alkyl. Now we have to see in beta hydrogen elimination the reverse. So can we have this methyl elimination? Okay, now because this alkene is inserted into the metal methyl bond. So can you get the reverse reaction? So this is the reverse reaction, okay, which actually does not happen. Okay, because the methyl elimination is very, very difficult. So what happens here? As this is, you can see this is a single bond. There is rotation around the carbon-carbon bond, so that the sterically crowded methyl group that is away from the metal center. So we can have a metal, this beta hydrogen rather it is eliminated than this methyl which is present on the beta carbon. So although we started with the elimination of, insertion of alkene into the metal methyl bond, so the reverse methyl elimination does not happen. Rather, this gives the product in which there is rotation around the single carbon-carbon bond. So this hydrogen is closer to the metal. Now there is elimination of hydrogen rather than the methyl group. So here we'll see an example. So this is the beta hydrogen elimination. As you can see, we can have this this hydrogen present on this beta carbon is eliminated. So we are having a metal hydrogen bond plus this alkene. So we have taken example in which, now you can see these are neutral molecules bidentate. So these are two ethyl groups which are eliminated. So now you can see the electron count. If you see here, it is iron 2 plus. This case it is iron 3 plus because there is plus 1 oxidation state. This is iron 4 plus. So what we are doing the electrochemical oxidation from iron 2 plus to iron 3 plus to iron 4 plus. Now we can see the reaction. What are the reaction? This reaction is, all these cases, this is 30 degrees Celsius, but look at this T half, that is a half-life period. For example, in the first case, this is 15 days. In the second case, this is 30 minutes. And in the third case, this is 10 to the power minus 3 seconds. That means the T half decreases drastically. Okay, and look at the product. What are the possible products? For example, in this case, the possible products, for example, if both the ethyl groups are eliminated. Okay, so the product ethyl means this is C2H5. So if both the ethyls are gone, so the product, what are the products? Let me write. This is, let us say, first product is C4H10. And if there is beta hydrogen elimination, you can have C2H4, or you can have C2H, okay, C2H6. So these are the three possible products. Okay. So this, now see, when both the ethyls are gone, okay, so we call, what do you call? Can you just name it? This is called reductive elimination. That means both the ethyls are gone, two groups are going away from the metal center, and there is decrease in oxidation state by 2 units. So that means both the ethyls are gone. So the product is C4H10. We call that is reductive elimination. Now the beta hydrogen elimination, the products are either, let us say, you can have this, let's say, MH bond. Now this C2H6 is forming. That means one of the ethyl and hydrogen are gone, and C2H4 is the alkene is gone, and you can have a metal hydrogen and metal alkyl complex. Okay, so you can see as the oxidation state goes from +2 to +3 to +4, this +4 oxidation state, the major product is C4H10, which is reductive elimination product. Because the oxidation state is +4, iron +4 is not stable. So that is converted to iron 2 plus by reductive elimination process. Okay, but when the oxidation state is low, that is +2 oxidation state, the beta hydrogen product, they are the major product. Okay, so this is the product which is eliminated. C2H6 is eliminated, and you get the metal hydrogen. Metal alkene is only bond. Okay, that means metal is connected to alkene, and one hydrogen and one ethyl group, they are eliminated as the major product. Okay, and in the middle case where there is +3 oxidation state, you can have this still the the reductive elimination is the major product in along with this beta hydrogen one. Okay, because it is in +3 oxidation state. So these are the things, which we discussed in today's class. We discussed about the reductive elimination. We discussed about this CO insertion reaction, or we discussed about the reverse of this insertion reaction, that is elimination reaction. So we'll discuss few more of these organometallic reaction in the next class. Thank you very much.